All right, we are live. Hello, everyone. Happy Thursday. I hope the weather is as nice where you are as it is here where I am. It's finally spring here in the East Coast area in Massachusetts. We're really excited today. We have a special guest, Chengji Yao from Google. He'll be covering some of the recent performance optimizations of vLLM on Google TPUs. I reviewed some of the slides. There's exciting graphs in there. It's just amazing how much performance the team at Google, together with Red Hat and the vLLM community, has seen over the last couple of months. So Chengji will show us exactly how that happened and what the next is in store for Google TPUs and vLLM. Michael, do you want to do a quick intro, and Chengji can also maybe do the same thing?
Yeah, hi everyone. Michael Goen here. I'm a principal engineer at Red Hat and a committer on the vLLM project. Hosting the office hours is what I like to do for you all. And yeah, today we're joined by Chenji. If you want to introduce yourself.
Hi everyone, my name is Chenji Yao. I'm a software engineer in Google, and I'm in Google's vLLM TPU team. And I'm very glad to be here. And I'm also a vLLM committer recently. Thank you.
Oh, there you go. We forgot to put down the slides. Well, congrats on becoming a vLLM commuter. I'll do a slight round of applause on my end at least. And since I always do forget to introduce myself, I'm Sasha Zelanovic. I also work at Red Hat with Michael, and Michael and I have been putting these office hours together for some time right now. Seems like it's been a year because it's number 24, but I'm pretty sure we started in June. So we're coming on our year anniversary, and thank you so much for everybody's support here. All right, Michael, if you want to go to the next slide, please.
Sure.
So guys, per usual, if you've been around, you know the drill. If you're new, we love to make these sessions interactive. If you feel like turning the camera on, please do so when we actually see each other in person, that we're not complete strangers. We do have a dedicated session, Q&A session towards the end of the office hours, but you can ask questions at any time. You can just unmute yourself and start talking, or you can submit questions through the Zoom Q&A chat. We'll make sure to get back to pretty much every question. I don't think in the last 24 sessions that we've missed one question, so please feel free to keep them coming. So you can find this recording actually immediately now on YouTube as soon as the session is done. So if you want to forward out your colleagues or want to review something, you can find it there. It's also, as of today, on Red Hat's YouTube channel, so check it out there as well if you want. If you have any follow-up questions, you can always reach out to Michael or I. My email actually is pretty easy. It's sasa@redhat.com. And I believe Michael is going, so you can always send us an email and we'll get back to you. Or even better, vLLM Developer Slack. The link is right here in the slides. So please join and join the discussion there. One thing that we love to do is we like to asking people where you are dialing in from. So if you pull up your Zoom chat right now, please, and let us know where you're dialing in from. There you go. Michael is from Boston. We've had many countries join over the last 24 sessions. You can see all of the flag emojis in the bottom right corner. So hi, Boston, Austin, Sunnyvale, India. Thank you for joining us from halfway across the world. Rio, hi, Max. Nice to see you again. I believe Max has been to nearly all sessions. He's definitely missed a couple, but he holds probably the most attended office hours aside from Michael and I. Bangalore, San Francisco, Toronto, Seattle, Palo Alto, California, London, UK. Welcome from London. We love seeing the international audience. Hey, New York City, Kevin, we're actually hosting a vLLM meetup there in a couple of weeks on May 7th. I think you have to come to represent office hours. Minnesota, hey, hello from Google. Florida. All right, thank you guys so much. So, Michael, I'll pass it over to you now.
Yeah, thanks a lot for the warm welcome, Sasha, and it's good to see everyone again this week. So what's been new over the past 2 weeks? I'll go over a new vLLM release that came out, 0.8.4, as well as some new blogs that came out. This release mostly focused on Llama 4 model-wise, and then also supporting in terms of bug fixes and performance optimizations. But there's also, of course, a lot new models supported, even unreleased models that have been supported. So that's fun to talk about. As we've already gone over, today's topic is going to be on how performance optimization for Google TPUs has happened for vLLM, particularly in the new V1 backend for vLLM for TPUs. So Chenji will give us a nice overview on that today. Upcoming office hours, we have the next one happening on structured outputs from Russell at Red Hat. He's a committer on the project that's been working on that feature for a while, which is a pretty important and interesting application user feature. And then after that, we'll have an introduction to Torch Compile, how that works with vLLM from Luca, one of the other engineers at Red Hat, and also Richard over at Meta on the PyTorch team. Of course, Torch Compile is used a lot for the TPU backend, which Chenji will get into. So that should be an interesting one to see alongside this. And as Sasha mentioned, we're doing the first vLLM meetup in NYC in about 2 weeks. Registration page is live. I think it's getting pretty full, so definitely sign up now if you have interest in coming. So to kick us off, I want to first explain what vLLM is if you're not already familiar. It's a fast, easy to use open source inference server. It's the de facto standard. It has millions of downloads happening every week and month. It has tons of stars. I think we're actually over 45,000 stars now. It's a pretty linear, consistent growth. Over 1,000 unique contributors, which is pretty great for a library that's only about 2 years old. It's popular exactly because it supports a lot of models. We actually have even more model support that I'll show through one of the blogs that we're highlighting today from the vLLM project. Because of its popularity, it sees a lot of state-of-the-art inference optimization research landing in it, both from academia, also from industry, that fork vLLM and use it internally for their production workloads. And of course, it gets great performance on NVIDIA GPUs, but part of the reason why it's so popular as well is because it works and is performant across a large variety of hardware like AMD GPUs, of course, Google TPUs that we're going to talk today, AWS Neuron, Intel Gaudi, even some of the newer accelerators like Huawei Ascend, and it even runs on CPUs. So alongside all of that support, it also doesn't just run large text-only large language models. It also can run multimodal models, image, audio, video input, embedding models, reward models. So you can use vLLM inside of RLHF workflows, and re-ranking and scoring for even more advanced vector database usage. Of course, we also have many different types of quantization integrated in vLLM. There's a lot of the work we've worked on. We have custom kernels from Cutlass, Triton, integration with Torch Compile, as we already mentioned. And of course, many inference system optimization features for efficient scheduling or efficient caching to better serve user requests like chunk prefill, prefix caching, multi-LoRa batching for serving fine-tuned models very efficiently, speculative decoding, and increasingly disaggregated prefill and decode for large-scale distributed inference. Of course, it also supports many application features like tool and function calling, as well as structured outputs, which we'll cover in future talks, thankfully. And many different types of parallelism to scale your models across multiple types of, multiple amounts of hardware accelerators, and even across nodes as you scale into larger distributed inference. And Chenji's definitely going to talk about that with how parallelism works on TPUs. So a little bit about what Red Hat is doing with vLLM. We're a top commercial contributor to the project. I mentioned I'm a committer myself on the project, and we help enterprises scale their deployments of vLLM as they take the open source software and build their inference infrastructure on top of that. Here are some of the contributions that we've made to vLLM. We focused a lot on the performance side, as I mentioned, quantization, custom kernels for that, written in Cutlass and Triton. Um, and of course, we also worked on integrating Torch Compile initially into the project, and even using it for custom fusion passes. So, using it as a graph compiler, so we can keep the model definitions as really nice, Hugging Face style PyTorch code, but start, fusing operations like you would in a modern graph compiler, to get the real optimizations. We've also worked a lot on reducing system overhead. So, in the particularly the new V1 backend for vLLM, we've worked a lot as a part of that project to reduce the CPU overhead and overall increase the throughput performance of vLLM. So we're happy to see it adopted by the TPU backend as well. And we've also donated some projects like the LLM compressor and compressed tensors projects to make it easier to produce, quantized, compressed models, as well as publishing many different quantized models out on Hugging Face. So if you're using any of the FP8 or Int8 models out there, you're probably already, using things that we've produced. So. And of course, we use that in vLLM as the core to a lot of our products where people want to run a variety of models across a variety of hardware on cloud, on edge, wherever you want to run your models. vLLM is key to that, and a lot of our customers use it happily. So that's the preamble. Now to get into some of the details of the new things of the week. So there were two blogs released by the vLLM project. One about the transformers backend integration to vLLM. Like I mentioned earlier, of course, in vLLM we have custom model definitions that are compatible with Hugging Face models, but we've been working with the Hugging Face transformers team to make it so if we haven't ported a custom implementation of a model within vLLM, we can actually leverage the transformers implementation directly and basically just swap out the attention module that they're using for vLLMs. And this allows the models to plug into vLLM and start using, page detection and of course all the interface and features and tensor parallelism that you get through vLLM that you can't as easily get through transformers. There is a bit of a performance penalty because we're not able to use custom kernels for, all of the individual operations. But the performance difference is quickly decreasing, and we're expanding the amount of models this can run on. Currently, it's limited to text language models, but hopefully, we're hopeful that this will allow vLLM to run many more models going forward, even if we don't have the time to make optimized custom implementations of them for vLLM. So if there's a model you've been waiting for, definitely give it a try with the Transformers backend. There's another blog that actually just came out on how to do RLHF with vLLM as the core to speed up, the generation, the reward signals that are needed to perform RLHF on your models and improve it. It's been used for GRPO, like you would use for DeepSeek style reward distilling. And this blog specifically is how you can use OpenRLHF and use the vLLM backend for that. But there's also, of course, integrations with many other RL frameworks like TRL or vRL. So give those a check out if you're interested. Now we get to what's new in vLLM 0.8.4. There were over 180 commits from 84 contributors, 25 of those brand new contributors. So shout out to them. And as I mentioned before, this release really focused on a lot of bug fixes and optimizations for Llama 4. I won't really go into detail here, but a lot of it is sort of trying to get rid of many of the individual flags that you needed to enable for different scenarios of deploying Llama 4 models, and just overall trying to make the defaults better and more automatic for the users. As I mentioned, there were several new models supported. Qwen 3 notably has landed as an architecture where the model hasn't actually been released yet. So we'll definitely be ready day zero for that when the model finally decides to drop. Also, small vLLM, new multimodal model that's very small, nice for testing. And notably, the latest Gina embeddings model, this uses nomic-BERT architecture, which has been requested for a while, which is pretty great. And of course, the intern VL3 and GLM4 architectures, which have been very competitive multimodal models for their size. Recommend trying them out. There were a few API enhancements. The first one I want to highlight is we finally support Matryoshka representations for embedding APIs. So this means your output from your embedding model doesn't have to be a fixed size, and you can actually effectively quantize it down to smaller sizes for more efficient vector database storage. This is a pretty nice optimization for vector databases. And definitely been a requested feature. We've also landed support for integrating with Torch.io quantization from the Torch project. So always good to see more types of quantization supported. On the hardware side, there's been developments, of course, on TPU. Some of those we'll get into today with Chenji, also on Intel Gaudi. And specifically on the performance side, there's been still continued work on DeepSeek. We've been tuning some MLA overhead. Some more, we're putting in some custom kernels, and we've generally been trying to hook up more types of formats available as there become more types of quantized MOE models coming out there that we kind of rushed to add support for with Llama 4, and now we're expanding those more flexible types of quantization for MOE models to all the MOE models. So definitely look forward to hopefully seeing better accuracy for the quantized MOE models that we are certainly putting out on Hugging Face over time. There's been a lot of work on V1 backend to support more features. A nice quality of life feature is you no longer need to specify the number of multimodal items that the engine needs to support. This will happen by default. So the maximum number of multimodal items you'll be able to support for a single request will now just be strictly based on your max number of batch tokens and how many multimodal items you can fit in your encoder cache. And we've done several refactors to make this easier and optimizing multimodal behavior in V1 to also make it easier for other backends like TPU to implement them instead of just the initial NVIDIA CUDA implementation. We've also done a lot of work on enabling Eagle model speculative decoding. There's support for Eagle 1, and we're very actively working on supporting Eagle 3 right now. So that's most of what I wanted to cover here. I know it was a lot. Feel free to ask questions. I'll answer in the chat. But for now, we'll pass it over to Chenji for going over what's new with TPU performance.
Thank you, Michael. Let me share my screen.
Great, thanks.
Hi, everyone. I will talk about the performance optimization of vLLM on Google TPUs, especially for the recent 2 months. First, I'd like to say that all of this work is a collaboration between the Google vLTPU team and our partners in the vLLM open source community. And thanks to all of you first. In today's agenda, I will first talk about the actual performance enhancement to show how much we achieve for about the performance optimization, and I will also give you a brief view of the system about the software and hardware, and then I will show the detailed optimization work. In the end, I will talk about our future plan. Okay, so for the last 2 months, Basically, we most focus on the Llama 3.1 8B model and Llama 3.1 70B models. For this specific workload, which has 1800 inputs and 128 output. For the Llama 8B model, we can see more than 3x speed up compared with 2 months before. And for the 70B model, which was run on V6E with 8 chips VM, TPU VM, we can see almost 2x speed up in the recent months. And I'd also like to express my thanks to all the previous work in the vLLM TPU. Because of your work with such a solid base of the vLLM TPU infra, then we can focus on the performance in the recent 2 months. Okay, then let's take a look at the system overview. First, we can talk about from top to bottom. First, from the model level, we can use PyTorch op and the path kernel to represent the model. The PyTorch op is just nothing different from other native PyTorch op. And for the path kernel, path is a language similar to the OpenAI Triton. You can write TPU custom kernel using path. Because currently, some of the kernel cannot be easily written or cannot be easily optimized in the XA compiler stack, which is based on the HLO and the ALO. And then we will use PyTorch Dynamo to capture the model as a whole graph, which means that currently we only support the vLLM compilation mode of Dynamo once. We don't support the piecewise compilation yet. And the path kernel will be wrapped as a PyTorch custom op in the PyTorch Dynamo graph. And then the whole software stack is actually 2 layers of compilation. We will use PyTorch SA to convert the PyTorch FA graph to HLO graph, which is the input of the XA compiler. And for the original path kernel op, we will convert it from PyTorch custom op to HLO custom op. Then for the HLO custom op, we will use the software stack of class kernel generation. We will use the Mosaic and the ALO stack to generate kernel for it. And for other HLO operations, we will use the original XLA compiler stack from HLO to ALO and then TPU kernels. And we will do some graph level optimization on HLO like Fusion, and we will also do some low level optimization in the ALO. For some TPU basics, it's actually very, very basic. It's very simple because we don't have too much to go through all the TPU knowledge. So first, TPU has some difference compared with GPU, NVGPU. TPUs are basically sequential machines, which means that we don't have too many. We don't have the concept of threads in NVGPUs, and it also means that most of the optimizations we can apply on TPUs are vectorizations. Because TPUs are sequential machines, with very large vector registers, which is 8 by 128 of 32 bits. And some exception is that in some generations of TPUs, we have mega cores. For example, you may see that if you are using V5P TPU, you may see that there's a VM type like V5P-8. It means that it has 4 V5P chips and 8 V5P cores in total, which means that each chip have 2 cores. But generally speaking, it's not that wrong to say that TPU are sequential machines. The second important thing is that the last 2 dimensions are treated very differently. As I mentioned before, the register has the shape of 8 by 128. So it means that if we want to apply some operations on the last 2 dimensions, like reshape, transpose, and other layout or shape adjustment operations, usually it's not free. And all vector computations is padded to 8 by 128 tile size, because we have to the smallest unit of computation is the register, and the register has a size 8 by 128. Here for in the right graph, for a tensor with the shape 12 by 320, we have to use 6 registers for it, and we have to pad the tensor to a multiply of 8 by 128. Okay, this is the basics of the software and hardware stack, and I hope it can help you understand better why we need to do the optimization work this way. And in the optimization work, I will talk about these 5 components: record attention kernel, KV cache writing, recompilation fix, communication optimization, and we actually also benefit from other work in the vLLM community. For the record page attention kernel, first let's take a look at the kernel algorithm. For the Q shape, we have as token Q head num and head size, and for the KV page shape, we have page num, page size, combined KV head num and head size. Note here that the KV cache is actually combined together as one tensor, not separated as 2. And for the record page attention kernel, we use the Q tensor, and we use the cumulated Q length, which is used for the record information. And we also need the KV pages, the whole KV pages, and the KV length for each request. And we also need the page index to know this is essential for the page attention, for all page attention, when we actually also have other arguments. For the basic algorithm, so first, it's actually a lot of loops in the algorithm. And I already omit some of the loops from vmem to register to simplify it. So first, we need to know the Q block size, head block size, KV block size. Q block size and KV block size can be retrieved from the auto-tuning table. And the head block size is calculated automatically. Then we will get the current iteration from the current Q block and head block, and we will fetch the specific Q block from the HBMM to vmem. Then for each Q, because it's RAG, so maybe there are several requests in the Q block. So we need to iterate through the request ID. And then for each request ID, we need to fetch the corresponding KV blocks. know that because maybe the KV block, the whole KV cache is too large to fit into a VMem memory. So we have to also need to chunk it to several blocks. So for each block, we also have a loop here, and we need to load KV each KV block from HBMem to VMem. And after we get the Q block and the corresponding KV block, we need to do the flash attention for it and put the result in the output. And for each sequence request ID, actually we also have other scratch mem to store the intermediate memory or the scratch memory for the flash attention based on the flash attention algorithm. And we need to accumulate it for each sequence or for each request. And there are several main points I want to point out for the optimization of the regular page attention kernel. First, we use the layout of the Q and KV as token, head num, head size, instead of head num, token, and head size. By doing this way, we can avoid the expensive transpose for both inputs and outputs. Because as I mentioned before in the TPU basics, when the transpose involves the last two dimensions, it's not free, and it's actually a little expensive. And also, in this layout, Mosaic does not need to support arbitrary slice. Here, previously, if we put the token in the second minor, because token is ragged, so usually it means that it's arbitrary. But if we put the head num in the second minor, the head information is quite static, so it's quite so we only need to support static slice in Mosaic. The third thing is that for decoding requests, because each request only have one token, but also as I mentioned before in the TPU basics, the smallest unit of the register size is 8 by 128. So it's quite a waste because we have to do the metmor with the register with the size of 1 by head size, not 8. But if we put the head num in the second manner, especially for GQA, because because usually 4 or 8 Q head share the same KV head. So we can increase the metmor intensity by 4 or 8 and head size. Basically, it's the Q head, the ratio of Q head to KV head by head size. And to also, as we support stride loading, it makes us to support the layout this way because the attention algorithm is basically a loop over heads. So if we put the layout as token head num and head size, we have to do the stride loading. And luckily, Mosaic already support stride loading. Although currently the stride loading is a little limited, but yeah, we can improve it in the future. We also have other optimization. First, we can the KV cache is combined, and we can just load KV cache one time and just separate it into different registers, which makes us to save half of the loading from VMem to registers. And we also simplify the metadata calculation. We need the metadata because we need to know we need to know the mapping between the Q block and the sequence IDs. And we also make it the calculation on the fly to make it can be overlapped with other calculation or other unit, because there are, although TPU is a sequential machine, it has several units like DMA, SALU for the scalar calculation, vLLU, and MXU for the metamor, and also other loading parts like vector, register, and register loading. Okay, I just finished the optimization work of regular attention kernel, and then let's take a look at the KV cache writing. Here you may see the graph. It's actually from it actually represents one transform layer of a preview step in V0. And when we talk about the bottleneck of a transformer forward, maybe you cannot imagine that the bottleneck previously is actually KV cache writing. Here, the Fusion 4 and the Fusion 5 are KV cache writing, and they almost account for half of the time. And I did some calculation before. The bandwidth utilization is only 0.3%. It's mainly because, so first, TPU is not good at scattering, and the previous KV page layout is num KV head, num page size, and head size, which means that we have to do the 2 by token num by num KV head times of the scatter, and each scatter has the size of head size elements. For the optimization, so first we change the layout to num page size, num KV head, and head size. Basically, we just move the num KV head dimension to the second manner, and also we combine KV cache. Through this way, the KV writing frequencies is reduced to token num. In the meantime, we are also trying to optimize the KV cache writing further to make the writing by page instead of writing by token. It is only used for preview because preview has multiple tokens for each request, but in decoding, there's only one token. We have a prototype in V0, and we observe a 10x speed up, another 10x speed up. But for V1, it's a little tricky because preview and decoding are mixed together. So we are planning to write a KV cache writing kernel for it. Okay, the third thing is recompilation fix. So firstly, because the TPU software stack is a pure graph compiler solution, which means that everything needs to be compiled. Even though sometimes you may see the eager mode support no matter in JAX or in TouchSA, but it's actually just compile one operations, and also the compilation requires static shift, so it's quite strict, in my opinion. So we need to handle the compilation carefully because we don't want our user experience like that. For example, when we are serving one user, we don't want the vLLM TPU server to say that, hey, please wait 1 minute. Let me finish my compilation and then let me reply it to you. It's quite too long, and no matter the TTFT or TPOT, latency constraint cannot be satisfied, and it will also hurt the performance. So to fix the recompilation, so first we need to make sure that the topology of the graph in warm-up and graph in real execution are exactly the same. So this is thanks to the previous work in vLLM TPU, because we already support the touch compile or touch dynamo, and we have a OpenSA backend through the PyTorch SA solution. So that's why we can handle it elegantly, because we can use touch compile to make sure that the topology is exactly the same. If we handle it carefully, if we just make sure that we wrap the method which involve TPU computation in a touch compile. And we also need to make sure that no operation is involved in the input preparation. Because in the GPU code, you may see there's some slice operation, and to slice the GPU buffer to the exact size needed. But in TPU, we cannot do that, because usually the slice is quite dynamic. We have a lot of shapes, and so what we do is to first prepare inputs on CPU, which means that you do the slice and do the padding on CPU, then we transfer the data from CPU to TPU. And basically, we separate the graph to several different parts. We have the LLM backbone and the hidden state selection and the multiple sample graphs. And here I didn't mention here is the multimodality encoder, and we may have more in the future. And each subgraph, we need to make sure that the shape is padded, and we use bucket padding, and we need to trade off between the compilation time and the width of padding. Okay, the fourth part is the communication. First, let me talk about simply about the TPU network topology. So for a TPU pod, it's an ND torus network. For example, for a V6E pod, it's a 16 by 16 2D torus pod, and for V5P pod, it's a 3D torus pod. But usually in inference, we don't use the full pod. We just use a slice of it. So for the V6E TPU with 8 chips, usually it can be simply considered as a 1D ring. You can see that it's like that, although we have some more connections between this TPU and this TPU and this one and this one. But usually those two links are not that useful, especially when we do some communication, like all reduce, all gather, and then reduce scatter. Okay, let's take a look at the timeline again. So for the original communication timeline, it's a transformer layer on the Llama 70B model on V6E8. So you may also see that the all reduce actually accounts a lot of time in one transformer layer. It is mainly because the bidirectional ICR bandwidth is not large compared with NVLink. And you may see that in the V6E official page, the ICR bandwidth is larger, but that's actually the bandwidth of four directional in total, not bidirectional. But as I mentioned before, in a V6E8, it's can be considered as a 1D ring, and it's bidirectional. And I also calculated the ICR bandwidth utilization, and I figured out that it's only 55%. So it means that it makes things worse, especially when we consider the bandwidth bandwidth utilization. So then we collaborate with the XA compiler team in Google, and then we found that the ring algorithm is not optimal. Ideally, we should use a 1D ring, but actually we not. So we optimize it later. Also, we need to make sure that the ring order is optimal. We cannot make it very random. So basically, we need to make sure the ring order is compatible with the ring order. I mean the communication order is compatible with the ring order. So basically, we need to make it the order like 1, 2, 4, 6, and 7, 5, 3, 1. And in the with these two optimizations, we can increase the communication performance by more than 30%. Also, although we try to use collector maximal optimization, which is used to hide the communication overhead under computation, but we figure out that we cannot implement in a short time because currently vLLM only support MPMD, but the XC compiler stack is mainly optimized for SPMD. So yeah, so this is the work we will do in the future. The last but not least, we also benefit a lot from the vLLM community. First of all, due to the upgrade from vLLM v0 to v1, it actually benefits us a lot. It can help us save the scheduler overhead, and it also helps us to due to the mix of preview and decoding, we can actually save the wait loading time for those decoding requests because they are usually memory bound. Also, we received quite a lot of performance tuning suggestions from the community. And there are also about 10% performance gain from other optimization. Actually, I don't know what they are, but it's just I just remember some day when we wake up in the morning and we found that we suddenly have a very apparent performance gain, but we know that we don't have any optimization on our side that day. So thanks to the community, and I believe our vLLM TPU will also contribute more to the vLLM community, and it will not only limit to TPU. Okay, finally, let me talk about the future plan. So first, we want to make Python in vLLM more extensible for both model loading and forward, because currently the model loading is also actually quite coupled with the parent strategy. We will support pipeline Python, and based on the extensibility of vLLM, we will support pipeline Python, content Python, or maybe X Python, and etc. And we will also optimize multi-modality models. And we will also optimize for different use cases because different use cases have different input sequence length, output sequence length, and max model length. We want to make sure that our optimization can be generalized for most of the cases. And we want to optimize. We will also optimize compilation time. It's because currently the TPU essay compilation takes quite a lot of time, especially compared with GPU, and we will optimize it for both the first run and the second run. Because the second run can reuse the compilation cache if it is persistent. And we will also support the new generation of Iron 1 TPU in the future. It will, yeah. And there's actually also other work we will do, but I just don't list it here. Okay, this is pretty much of my my sharing.
Yeah, thanks a lot, Chenji. Definitely, we will have a lot more to share in the public roadmap in vLLM
Yeah.
as we particularly defined. Or do you want to stop sharing so I can
Okay. Okay. Sure.
share the slides? Yeah, sure. Okay. Yeah, well, I maybe had some questions on your slides, but does anyone in the chat or on voice want to ask questions? Okay, well, maybe some of the I had a question on yeah, I mean, I guess like kind of on this communication or rather connectivity in TPU. Do you see this staying like has this stayed like pretty consistent across generations of TPU and you think it'll probably stay in a similar way forward that you yeah, kind of stick with a torus structure? Um, or are there thoughts to expand on this?
I think it will. In my opinion, I think it will evolve together with the model and optimization. For example, as I know, currently MOE models are more and more popular.
Yeah.
So the basic optimization, parallel optimization for MOE model are expert parallel, and it requires all-tool communication.
Hmm.
Yeah, but for the torus topology, I don't think it's that good for all-tool communication. Because also it means that we every chip need to communicate with each all other chips, not like all duos together or reduce scatter. They can just communicate in a 1D ring or 2D ring ways.
Yeah, understood.
So maybe in the future we might see some network topology like that O2 network in. I mean the here O2 I mean is the network topology. So maybe we can see something like TPU switch in a TPU pod, and the TPU chips can communicate with each other through the TPU switch, just like the NV switch in the NV GPU.
Yeah, that definitely makes sense. Yeah, thanks for that thought. There's a question from Max on how long does it take to compile a model for the TPU backend? I know this changes, but maybe talking about maybe the structure of how a
Mhm.
model gets compiled.
Yeah. So first, it actually depends on model. In my experience, so first for a model forward, it takes about for one graph, takes about maybe 5 seconds to 10 seconds. So so for usually we have to compile for about 10 graphs. So for this, it might take 2 minutes in total. And we also need to compile other components like multimodal encoder and sampler. So, but usually that parts are not very large. So just general speaking, we might it might take about 2 to 3 minutes in total.
Yeah, definitely the model, the like LLM backbone forward in this diagram here is definitely the majority of the time. And that's also the case for NVIDIA GPUs as well when you're compiling CUDA graphs and also compiling torch compile nowadays. That this takes, several seconds. It can take minutes, particularly for larger graphs. Um, yeah, any other questions? Yeah, so one question I had actually with the ragged page attention kernel, I thought you explained this rather well with the benefit of bringing token inside as an inner dimension rather than the first dimension. However, I guess like is this now a restriction that you have that the head num needs to be divisible by 8, I guess?
It does not to be divisible by 8. For example, the Llama 17 model, the Q head num is 64 and the KV head num is 8. But with tensor with TP equal to 8, so each chip for each chip the Q head num is 8 and the KV head num is only 1. Yeah, so we can still do that if the head num is not divisible by 8.
Yeah. Does this introduce waste though, since you mentioned that the head dim is like having the head dim here allows for filling those registers?
No, because the ratio of Q head num to KV head num does not change. It's still 8, even we short the.
Oh, right.
Right.
Okay.
But
Yeah,
it might wait some. It might wait. It might make the performance of KV cache writing not that good because it makes the size of each writing smaller.
right. Yeah.
Yeah.
Yeah, so there's another question on, is prefix caching supported? How large is the storage for prefixes and how performant is it? Have you expanded external KV cache storage? Experimented with external KV cache storage?
So yeah, thank you for asking. So first, prefix caching is already supported. And secondly, currently we don't support other KV cache storage. Yeah, but it's in our plan. We just need to figure out the priorities. It depends on whether is there a lot of customers requiring it.
Yeah, okay. There's another question on, I've noticed the vLLM TPU Docker image is about half the size of the normal CUDA image. That's a really easy question. The dependency tree for CUDA is very heavy, compile a lot of binaries. It's very intense. So yeah, it's just luckily we kind of compile a lot more things at runtime. Yeah, basically for the TPU backend. How does the kernel manage numerical stability or softmax for extremely long or short sequences? I think this is kind of like more of like a how does flash attention work question.
Yeah, so first for the flash attention, there's a MATMOR, softmax, and MATMOR. So we will accumulate the softmax in FP32. So yeah, we use this way to manage numerical stability, to just promote up to float 32. I think it should be the same, or we use a similar strategy as other hardware, other implementation of flash attention like NVGPU.
Yeah, I think so. A question from Ford, what about disaggregated architecture? Are these still relevant for TPUs? So I think this is referencing like disaggregated prefill and decode. Do you see this as being different to consider?
Yeah, actually, we also plan to implement disaggregated serving, and there's some difference between GPU and TPU. So I think it's mainly it can be talked about based on the software and hardware. For the hardware, due to the so first we have two network in TPU. One is the SCI. It's the communication, it's the link inside one TPU pod. And another one is DCN. It's the communication between TPU pod. So we need to figure out that whether we should use SCI or DCN. Secondly, because as we mentioned before, the TPU pod has the ND torus. It's not an O2O network. So, but maybe the communication in the disaggregated serving might be a little arbitrary. So we also need to consider both the bandwidth and the network topology. For the software side, because maybe there's some the TPU software stack is the pure compilation based stack. So we need to make sure that at least there are no expensive compilation in the process of the disaggregate serving, because there's still some slice off, and because we need to slice the key cache and transfer it to another node. Yeah. So there's some challenge and something special to support disaggregate serving in TPU.
Yeah, okay, good question. Well, we are over time, but maybe we can have one more question from Wenlong. Is the TPU optimized kernel the biggest difference from GPU usage? Is there any other optimization that could be especially set for TPU serving?
I think one important the kernel is the one important challenge, and the other one is on the AI framework side. It's the comparison-based solution. So you may see that the TPU model runner is a little different from GPU model runner, and the sample implementation and the input data preparation code is also different from the GPU side. That's also a challenge. And after we support more and more features, and we need to handle the differences carefully.
Yeah, well said. Well, that's all we have for today. Thanks for the nice questions and discussion, and of course the presentation, Chenji. Really appreciate you going into that detail. We just want to close things off as we always. Thank you for being a part of the vLLM community. Continue to ask questions, open issues, contribute to vLLM features. We'd love for you to be active in the GitHub, either commenting on issues or PRs in flight that you would like to see get priority, or features that you're interested in that you don't know if they're in flight or can just get into our roadmaps a bit faster. And of course, build things on top of vLLM. Tell us about it. We're happy to help promote and make you a part of the project. As always, give us any feedback, either in the vLLM Slack or letting us know directly within office hours if there's anything we can do to better serve you and help make these office hours better. As we mentioned before, the next vLLM meetup is happening in New York City. Make sure to sign up in the slides that are shared here or on the vLLM README. And we're hiring at Red Hat. If you want to work on vLLM, we're continuing to work with the TPU vLLM team. And we're just happy to be here and happy to be a part of the community. So thanks, everyone. Hope you have a good, productive rest of your week, and take care.
Thank you.
Bye.